Vande Gujarat. Happy New Year to all the viewers, dear students, if faculties are there. This is the first lecture in physics, or you can say especially in electronics for this year, and I am feeling very happy to deliver it to you. I will try to explain some fundamentals about the transistor circuits, how they are analyzed, and what are the parameters which are important or more used in general cases. So today we will talk about the transistor circuits with respect to the H parameters. H parameters, what they are, and how they evaluated for a particular transistor or as an amplifier as a whole, that we will try to find out. So let us start the today's lecture. Okay, so go to the slide. I would like to introduce myself. I am Dr. T.H. Patel from VP Science College. I am the Associate Professor in Physics, and that's it, my work that you will evaluate, and we go for that. Okay, let us come to the first slide now. Today we will try to cover the following topics: transistor operation modes, its characteristics, performance parameters, and some analysis methods. Then about the H parameters derivation by considering transistor as a two-port system. From that we will define what are the H parameters for a particular transistor in a particular mode, and then we will go for the equivalent circuit of a transistor using that H parameters. How H parameters, once we know, can be measured in a particular mode, that will also be discussed. Now another methods such as equivalent circuit method for a common amplifier circuit using H parameters, that we will also discuss, and finally some definition regarding common emitter transistor amplifier, that we will see. At last we will take one example and we will go for the summary what we have discussed today and what are the outcomes. So I am introducing you first of all the transistors, as we know very well. Okay, a transistor is a three-terminal device. Okay, a collector, base, and emitter. If we take N, P, N structure, N means N-type semiconductor, P means P-type semiconductor, that we know very well. If the construction is like this, then we call that it is a NPN transistor formation. And second possibility that you can see in the second image, that is a PNP structure with central base as a N-type. So these are the two main structures of the transistors that we know. Symbolically they are represented in this way. You can see that here we have 1, 2 and 3 terminals, a circle and the symbol. The arrow over here that distinguishes the emitter from the rest of the two terminals. And likewise in case of PNP, we distinguish or we use an arrow to distinguish the emitter terminal from the rest of the two terminals. This we have studied earlier. So let us go ahead. Now these are the pictures of some transistor. You may have performed experiments with transistors in your laboratory, but maybe the transistors are there within the box or you are not able to see them. So that's why this picture I am presenting to you. Just you can see different kind of transistors. Once you see here a 3-leg terminal, second another 3-leg terminals. So different kind of transistors and different shapes are also possible with them, but these are the, you can say, a general picture of a transistor. Now as it has 3 terminals, a transistor can be operated in 3 modes via keeping one of the 3 terminal common. For example, in the figure we can see that a base terminal is kept common. One section that is forming a input section, that is emitter and base. Another we call is the output junction formed via collector and base. So this was a symbolical representation of common base circuit of a transistor. If you look at construction wise NPN transistor, how it looks, that we can see in that. Okay, here you can see the currents also, the direction of emitter current, the direction of collector current, and the base current. You are also saying these two batteries VEB and VCB. Now what these batteries are? Why we connect them? We know that the transistor cannot perform operation without any energy. So we supply DC energy to it, and normally we referred it as a DC biasing of the transistors. So these two batteries, particularly VEB and VCB, they bias the transistors, and they are called as the biasing components of the circuit. The second case, you can say, when we kept emitter common, as you can see in this figure, okay, that if you keep emitter common between the base emitter, then and the second junction, you can say, or the second section, collector and emitter. So these are the two junctions, the output junction between collector and emitter, and the input junction between base and emitter. We call it as a common emitter circuit. And you can also see here how by using different biasing circuits, a common emitter voltage amplifier circuits can be fabricated. That I hope that you have come across this kind of circuits in your study. Now the third mode, we have seen the common emitter mode, common base mode, and the third terminal of the transistor collector, so common collector mode. So how in common collector mode the circuit can be drawn? I am assigning you as a homework. Go through the books, you find out how the common collector transistor circuit is drawn and how it looks like. A little bit assignment to you. Okay. Now we are switching on to the transistor characteristics. We have seen what is a transistor, and now we will switch to the what are the characteristics that a transistor can give to us, because they are very important and their characteristics decides this application. Okay, go to this slide. We are going to this next slide. Okay, the transistor characteristics, actually what they are, it is nothing but the graphical representation of relation among different currents and voltages. We know, we have seen in the earlier figures that there are many currents and voltages associated when a transistor is operated, either in common emitter, common collector or common base mode. So if we interrelate them graphically, whatever comes out we call is its characteristics. Okay, so what we mean by transistor characteristics, be clear that it is nothing but the graphical representation of the current and voltage. Normally they are referred as the static characteristics curve. Okay, now since we have two junctions, input and output, or we can say two section, input section and output section of the circuit when transistor is operated, we label two types of characteristics. One, the input characteristics. What is that? The input characteristics is nothing but the curve of input current with the input voltage when we keep the output voltage constant. So it is very easy to remember, a input current and input voltage when output voltage is constant. So graph of this, that we call is as input characteristics. Likewise output characteristics. Now if you think logically, then again you can answer what is the meaning of output characteristics. That it is a curve of output current with output voltage. Now at a constant input, but mind well, at this time we are keeping the input current constant. In earlier case, in the input characteristics, it was the output voltage which was kept to be constant. So input characteristics and output characteristics, these are defined in this way. Now this each of these characteristics, either input or output, they may be different for different transistor a little bit, but if you change the mode of operation, that is common base, or common emitter or common collector, then each mode has its own set of characteristics, and these characteristics leads to the application of a transistor in a particular device for a particular purpose. Okay, so these curves in a particular modes are very important. They are used to study the performance parameters, and the performance parameter, just like our body has some parameters, physical parameters like that, that decides our applicability for a particular event, maybe, or anything like that. Okay, everybody has its own identifying points. So likewise, transistors are recognized or identified via their parameters, and these parameters can be determined from this kind of transistor characteristics. So characteristics leads to the knowledge of the parameters, and these parameters later on decide which kind of application a particular transistor in a particular mode can have. Okay, so we need to find out the parameters. Okay, now which are these parameters generally? The input and output impedance of the transistor by itself, what is its current gain and what is its voltage gain. Okay, so these are the four main parameters. Once again I am repeating: input and output impedance, current gain and voltage gain. Now apart from that, sometimes bandwidth is also important, particularly when a transistor is used in a circuit where communication purposes or amplification purposes are to be performed or to be carried out. Now to determine these kind of parameters, that what a particular transistor has what kind of parameters, what are the values, okay, we need to analyze the circuits. By the analysis of that circuit, we come to the knowledge of the parameters. Now there are many methods that we can apply to know the performance parameters, or you can say to analyze the transistor circuit to determine the input impedance, either current or voltage gain, or its output impedance. Now mainly equivalent circuit method and graphical method, these are the two widely used method. Okay, once again, in graphical method, characteristics curves are used to find out the parameters, and that is some tedious. We must have the corresponding characteristics for that transistor, either input or output, and from that graphs we are able to find out the H parameter values, okay, or any other parameters value. Now the equivalent circuit method, again, that should be carried out in two ways. One is the AC equivalent circuit method, by which we can analyze the circuit, and the second one, that is the H parameter model. So now we come to the point, H parameter model, and that what we are going to find out about that. So two methods for analysis to know the parameters, either AC equivalent circuit and H parameter model. Now generally H parameter model is preferred. Now why this H parameter model of the circuit is important? Okay, or in other words you can say why H parameters are important. Let us find out that. Now while trying to knowing about the H parameters of a particular transistor, we should consider transistor as a two-port network system. Okay, here we can see a PNP and NPN transistors. Okay, we can consider this, either of this, as a two-port system, as you can see in the figure. A two-port circuit or a two-port network, you can call it. The two-port circuit, it is a transistor, it has a three terminals. I can show you like this, that this is the first terminal, this is the second terminal, and this, you can see here, this terminal is the common, the third terminal. Just like a transistor can have three terminals, we can kept one as common and rest of the two forming either input and output sections. So likewise here, we consider that the bottom line or the bottom points, this V1 line, this is a common line, this line, where the current flowing through the two-port circuit carries a current I1 when a V1 voltage is applied, and likewise this line, another port which carries current I2 when a voltage V2 is existing between that two. So this is the one port of the network, and you can say this is the another part of the network. Okay, so a two-port network is like this, and we exactly consider it like this. Okay, one more thing, that it can be the common terminal here, it can be either emitter, either base, or a collector. We are not sure right now what is there inside it. We don't need to worry about it. Just we keep one of the terminal common like this, either it can be emitter, collector, or base, and likewise the rest of the three. Now as we can see, there are four variables in this figure. V1, you can say this is the input port, say, then it is the input voltage. V2, you can say that is the output port, so that is the output voltage. I1 current, that is the input current. I2, and that is the output current. So these are the four variables. Now we can relate all these four variables in different ways. There are many possible ways, as you can see here, 1, 2, 3, 4, 5 and 6. There are 6 different ways in which we can arrange these 4 variables, while keeping 2 as a dependent and 2 as an independent variable. Now if out of these four parameters, if I select I1 and V2, once again I1 and V2 as an independent variable and V1 and I2 as a dependent variable, then whatever current relation we obtain and what the parameters we generate, they are called as the hybrid or H parameters of the circuit. So what are the H parameters now? Okay, we are able to define it. So out of these 6 possible ways, the 4 variables we can relate in a spatial way. Okay, like this. Let V1 and I2 be dependent and I1 and V2 be independent. In that case, whatever relation we will obtain, they are called, that relation is represented by some constants. Okay, for example, the input voltage Vi or V1, as you can see in the two-port network, can be represented as a combination of the another 2 independent variables I1 and V2. So V1 can be written as some constant multiplied by I1, the independent variable, plus some constant multiplied by the another independent variable V2. Now if we label these 2 constants, then here we call this as H11. Okay, we call this another as H12. Likewise, in a similar way, we can represent I2, okay, that is the output current, as a combination of 2 independent variables I1 and V2. I1 multiplied by some constant, V2 multiplied by some constants. So I2, that is equals to, we can represent like this, H21 a constant into I1 plus H22 another constant to V2. So this is one of the way out of those 6 ways that we have seen in which we can relate the 2 parameters V1 and I2 which are dependents. So such parameters H11, H12, H21 and H22 which relates the 4 variables of the 2-port system by above equations are called as hybrid parameter or H parameters. Okay. Now what are the units of these parameters? We have already defined H parameters. Okay. So here we can see in these 2 equations H11, H12, H21 and H22. These are the 4 H parameters now. Okay. Now what are their units? Okay. Now let us focus first of all on the first constant H11. Okay. The H11, if you look at this equation, okay, that V1 equals to H11 I1 plus H12 V2. What we find out? That V1 equals to something plus something. That 2 something means they must have a unit of voltage. It's a linear combination of 2 terms. The first term, you can say H11 I1, therefore must have a unit of voltage. Okay. Now since I1 is the current, we know the ampere is the unit. So what left with H11 then? What should be the unit of H11? H11 must be ohm. So that if the unit of H11 is ohm, then when ohm is multiplied by ampere, we will get a voltage. So this is how we designate the unit of a particular H parameter. So H11, the first H parameter we can say, it has a unit of ohm. Likewise, second parameter, H12, okay. Now it is already multiplied by with the voltage, okay. So H12 should not have any unit because V2 is already voltage. So H12 is unitless. And now you can easily derive the unit of H21. Okay, once again, now I2 is the linear combination of 2 terms, H21 I1 plus H22 V2. Since now I1 is already a current, okay, H21, okay, has no dimension, quite clear, or no unit. So H21 is unitless. And finally, H22. Now we know that I2 current is written as a combination of voltage and some constant. So that constants must have a unit which is reciprocal of resistance, and we know that very well, it is mho or Siemens. So these are the units, different units of different H parameters that we just define. Okay. Now actually what they define, if you look in the equation 1 and equation 2, we have all these 4 parameters for a 2-port system. What H11 defines actually for a 2-port network? Let us find out what is it. Now for the time moment, consider that the voltage V2 in this two-port network is 0. That is, output voltage is 0. Let us consider that. So what we get then in that case? When V2 equals to 0 means we are short circuiting the output terminals. So by doing that, what we get in equation 1, that as V2 equals to 0, we get V1 equals to H11 I1 only. And therefore what we get? H11 equals to V1 over I1. Mind well, when V2 equals to 0. Now H11 equals to V1 upon I1 when V2 equals to 0. Already one of the H parameter is there. Okay. Now since it is the ratio of voltage to current, that we know. Okay. And again, it relates the input quantities or first port quantities in this two port network. We label it as the input impedance of the device or two port network and designate it as HI. H for H parameter and I as it indicates the input impedance. Now using same logic, or you can from the same mathematics, we can find out what H21 equals to 0. So by placing V2 equals to 0, what we find it out that H21 equals to I2 by I1, a ratio of output current to the input current when V2 equals to 0. And normally output divided by input, that we labeled as the gain. So here H21 represents the ratio of output current to the input current of the two-port network system, and that is called as the forward current ratio. Once again, H stands for the H parameter and F stands for the forward current ratio. Now let us see another two parameters. Now let I1 equals to 0. That is when input is open. We make the input circuit open. Okay, so that the current I1 becomes 0. In that case, equation 1 gives us what? That H12 equals to V1 by V2, because I1 equals to 0, so H11 I1 equals to 0. So what we left with? That is V1 equals to H12 V2 only. Okay, so H12 equals to V1 by V2 when I1 equals to 0. Now what is V1? Input voltage. What is V2? Output voltage. So normally we know the ratio from output to input. Okay, but here it is the ratio of input to output. So we call it as the reverse voltage ratio, HR, and R stands for the reverse voltage. And now the last one, H22. From equation 2, when I1 equals to 0, we have only I2 equals to H22 V2, and therefore H22 equals to I2 by V2 when I1 equals to 0. Now if you look at here, we will find H22 as the ratio of I2 output current divided by V2, that is the output voltage. Normally what we observe? Voltage divided by current as a resistance. Now it is the reverse of this. Okay, so you can say 1 upon R like that. Okay, and that we know that that is called as the admittance. Okay, so H22 here in this two-port network system represents the output impedance. Now you know what is O in HO. H parameter, O representing the output impedance. So here we can list now all H parameters and what they define. Once again, H11 input impedance of the network, H21 forward current ratio, H12 that is the reverse voltage ratio, and H22 that is the output impedance, respectively HI, HF, HR and HO. So that is how we can generally describe them or how we define them. Okay. Now as I told you that we don't know what the actual two-port circuit contains, a transistor either in common emitter mode, common collector mode or a common base mode. Now let us consider that the transistor is in CE mode, as you can see in this figure. Okay, so what we get here, that the emitter, that is the common terminal, okay, the input terminal, that is input port, is consist of base and emitter, and the output port is consist of collector and emitter. So that is the simple analogy, and we get now as I1 as IB if you compare terminal to terminal. Okay, V1 as the base voltage or voltage between base and emitter, I2 as collector current and V2 as VC, that is the collector voltage, or VCE, the voltage between collector and emitter. Now we can rewrite our earlier equation using these notations, that is for this CE mode, for a CE mode transistor. Okay, we can write in this way: V1 equals to HI, H11, that is referred as now HI, I1 plus HRV2, and likewise I2 equals to HFI1 plus HOV2. Now these two equations, now for CE mode, we can represent in this way. Look at the equations carefully, that V1 is designated as VB and I2 is designated as IC. By comparing these two circuits, means a two-port circuit and a transistor common emitter, these two circuits, we find out the equations for the H parameters as the first equations that relates the input voltage VB, that is equals to HIE IB plus HRE VC. IC equals to HFE IB plus HOE VC. Now here in last equation, this last equation, we have used a suffix E. E stands to indicate that these H parameters are for a transistor which is operated in common emitter mode. Okay, so everywhere with HI, HR, HF and HO, E is incorporated to indicate that the transistor is operated in common emitter mode. If it is a common base, we can have HIB, HRB and likewise. Right? If it is a common collector, we have HIC or HRC or HFC or like that. Okay. So E here indicates the mode of operation of the transistor. Okay. Now for a CE mode, already we have defined that and what they represent, which current to which current. Just an analogy, that input impedance, that is the base voltage divided by base current. Forward current ratio, that is collector current divided by the base current. Reverse voltage ratio, base voltage divided by the collector voltage. And the output impedance, that is the collector current to the collector voltage. So these are the four H parameters represented in terms of different current and voltage for a common emitter mode. Now look at some basic designated values of the either common emitter or common base or common collector mode. HI, HR, HF and HO. These are the H parameters. Now if, for example, we have a common emitter mode, then the ratio VB to IB, that is called as the HIE, that is the input impedance. Likewise, if it is a common base mode, then the ratio of collector current, okay, to the emitter current, that is called as the HFB. Okay. And if it is a common collector mode, once again we have HRC, that is the ratio of base voltage to the emitter voltage, that is reverse voltage ratio. So this table illustrates various kind of H parameters or their designation, either for common emitter, common base or common collector mode. I, R, F and O, they are with H, and the rest, the second prefix, either E, B or C, that goes with the types of mode. Now normally once we know the H parameters, they are used to develop a circuit of a particular transistor, okay, to know its performance. Now let us find out how an AC equivalent circuit of transistor can be obtained using H parameters. Now we have one equation, we have two equations relating H parameters on a common emitter mode, and I have shown here VB equals to HIEIB plus HREVC. Now if you look at these equations carefully, a base voltage is a summation of two terms, HIEIB plus HREVC. Already we have assigned the units of the H parameter, what is HIE and what is HRE. IB, that is the base current. Now how we can draw a circuit that represents this equation, VB equals to HIE-IB plus HRE-VC. Okay. Now the input part of the transistor we have taken, that consists of base and emitter. Okay. So the voltage, input voltage to the base and emitter, that is VB, that is sure. So we can label it as like this. Okay, be careful. VB, that is the voltage, input voltage, that is between base and emitter, that we designate like this. Second term, HIE-IB, we know that HIE represents the impedance or resistance, and when it is multiplied by with IB, means when a current IB is passing through HIE, okay, it represents a voltage equals to HFE-IB. So we designate the term HIB-IB in the circuit like this. And now the second term, HRE-VC. Now VC is the output voltage and HRE, that is the reverse voltage ratio. We know that HRE is unitless because it is the ratio of two voltages. Okay. So what we left? That VC, a voltage multiplied by some constant. So the term HRE-VC represents a voltage which is given by HRE-VC. So in this way we can develop an equivalent circuit of the input section, because it is a hybrid input equivalent circuit of the transistor. You can say it is a simple Kirchhoff voltage law, and then just we draw the circuit that suits to that equation. Now let us focus to the output section also. For the output section, we have the collector current equals to HFE-IB plus HOE-VC in terms of H parameters. So here the collector current is flowing through the output network or output port, as we know that. So I have shown here collector and emitter here, and a current IC flowing through it. Once again, this equation represents combination of two terms. The first term HFE-IB, okay, and the second HOE-VC. Now naturally on the left hand side we have a current, so these two terms must represent a current, and now we know what is HFE and what is HOE. The units of that are known to us. Now HFE, again it is a ratio of two currents, so it was a unit less, and IB, that is the base current. Okay, so a base current multiplied by some constant. Okay, so we represent HFE-IB, okay, like this. We represent HFE-IB like this, a constant current, or like that, or which depends on the base current if it is changes. So the first term, okay, and the second HOE-VC, another current. We know the Kirchhoff current law. You can see in this animation on the one side, okay, right, on the left hand side you can see this, that three currents I1, I2 and I3, three equal currents I are coming to the junction, and when they are added, the resultant current we get this 3I. So this is the circuit representing what? 3I equals to I plus I plus I. So likewise we can draw a circuit which represents IC equals to HFE-IB plus HOE-VC. Okay. So the first term that we have designated, now we are left with HOE-VC, and that can be designated like this: HOE, the output admittance, okay, and VC. So a voltage, a parallel admittance with a voltage, and that satisfies the equations or the term HOE-VC. So we have seen how H parameter equivalent circuit of the input of a transistor and output section of a transistor can be drawn. Okay, so how we can find out the overall circuit of a transistor, input section as well as output section of the transistor? How the whole circuit can be obtained? Let us see that. By connecting the earlier two circuits. Now I have seen both of the circuits here, the input section circuit and the output circuit section. Both I have shown to you. Okay. Now simply by connecting these two circuits via their common terminal like this. Once again, these are the independent circuits and this is the connection. The common terminal is connected. So by using these simple connections, we can obtain the complete circuit of the transistor using H parameters. So this circuit, you can say, now emitter is common, base and collector, different currents and voltages are there, and different H parameters can be seen in this circuit. This circuit is called as the AC equivalent circuit of the transistor using the H parameters. These H parameters thus are helpful to designate the activities of the transistor at the input port as well as the output port. Now, for a transistor, these are the typical values. What is H11? That we have defined already. So HIE for a transistor normally is of the order of kilo ohm, 1 kilo ohm or so, not more than that generally. The forward current ratio, okay, 2.5. HFE is of the order of 50. It is wrongly mentioned here. Forward current ratio HFE is of the nearly equals to 50, and reverse voltage ratio is extremely small, is 2.5 into 10 raised to minus 4. Take care of this. Forward current ratio is is of the order of 50, 100 or even more depending on the transistor, and the reverse voltage ratio, that is very small, 2.5 into 10 raised to minus 4. And the output impedance, it is of the order of kilo ohm. If we think in terms of admittance HOE, that is the microsiemens, 25 microsiemens, and in terms of resistance 1 upon HOE, that turns out to be 40 kilo ohms. So these are the typical values of the transistor H parameters generally used in the laboratories. Now how these parameters can be measured? 4 parameters: input impedance, output impedance, forward current ratio, reverse voltage ratio. How they are measured? Let us see one by one. Okay, first H11, the input impedance, and for common emitter we know it is the ratio of base voltage to the base current, HIE. Okay, so using these characteristics, this is nothing but, you can say, a graph of IB, that is base current, against the base voltage. So this is the input characteristics. So from the input characteristics of the graph, characteristics of the common emitter transistor, we can find out HIE. How? See how it is defined: change in base voltage to the change in collector current when the output, that is collector to emitter voltage, is constant. So keeping the output voltage constant at a particular one value, we can find out a particular change in the base current, like this delta IB, for a particular change in input voltage, that is VBE. So by exactly counting these values and putting in these equations, we can find out HIE. The next, H21 or HFE, forward current ratio. As we can see, it is the ratio of change collector current to base current when the output is constant. Okay, so HFE, delta IC, change in collector current to the change in base current when the output VCE is kept constant. So for that we can use these characteristics. IC, that gives us delta IC. Okay, you can say this is the output characteristics of a typical common emitter circuit. Okay, here you can say this characteristics is for one IB, say 33. This characteristics is for another IB, 13 microampere. So we can go from these characteristics to these characteristics, and we can find out what is the change in base current, that is delta IB, and correspondingly the currents here, the second current, collector current, and the first collector current. So this gives us delta IC. So using this output characteristics, we can find out HFE of a transistor in common emitter mode. The third one, let us say HRE, reverse voltage ratio. For that we use the relation between the base current once again and the base voltage. We can say that is like a input characteristics of a particular transistor. Delta VB upon delta VCE at a constant base current. So here at a particular base current at operating point or nearby that, we can find out delta VBE, change in base voltage. See, with these different characteristics here, we can find out delta VCE for this to this, and then delta VB corresponding change here. Okay, so here from these characteristics we can find out HRE. And the last one, H22, the output admittance. Okay. So from these characteristics, you can say it is the output characteristics delta IC upon delta VC. So that is the change in collector current. You can measure on the x-axis for a particular characteristics. Take collector current corresponding to this point. Take collector current corresponding to this point, and we can find out that change in collector current for particular IB, and corresponding values of the output voltage and the another output voltage. So change in this from this to this, that is delta VCE. So from using these two values we can find out HOE. So this is how we can find out the values of the different parameters. For example, for a transistor 2N3904, the typical values of the H parameters are like this. The input impedance HIE ranges from 1 to 10 kilo ohm, minimum to maximum. The voltage feedback ratio likewise 0.5 to 8, 10 to power 4, and small signal current gain 100 to 400. As we mentioned earlier, normally it changes from 50 to 100, 200, 300 like that. So these are the normal values of the H parameters. Now, so far we have seen the transistor circuits, equivalent circuit of the transistor using H parameters. Now there are other methods also that we will see later on, but now when this transistor is incorporated, okay, in an amplifier circuit, what happens, okay, to the circuits? That also is of very importance. Now let us see first of all AC equivalent circuit method, just how it is used to analyze the transistor. Now here in this figure you can see a small signal amplifier, okay, consists of R1, R2, RC, RE, a voltage source, a source resistance, and a capacitor. Now what this circuit is, a small signal amplifier. It is using a voltage divider network. As you can see, R1 and R2 are the two voltage divider resistors. They bias this transistor, and at high frequencies these capacitor, coupling capacitors, this one and another this, we assume that they are short circuited, as happens normally as the reactance is very small. So at high frequency we can consider this two capacitor as short circuited, and we come to a circuit like that we can see. Now, so at the input between base and emitter, what we find out here, okay, if we neglect the DC sources, since we are interested in AC analysis, okay, what we find out that between the base and emitter, that is a small resistance appearing, and if you take the input characteristics, it is just like a PN junction diode, okay. And now if you look at the characteristics, the ratio, or you can say the ratio of this voltage to the current, input and output, represents a simple resistor, we know, a forward resistance, okay. So between base and emitter we consider that a small resistance exists, and we call it as Ri. So Ri, that represents the input resistance or impedance, you can say, of the transistor, and that can be seen from the characteristics. Next, what is at the output? So between collector and emitter, then this is the output characteristics. What we find out that if you look at the output characteristics, that at a particular base current, okay, it increases slowly and then it becomes almost constant, okay. So it represents once again a constant current source like that, which depends on the particular value of IB. So that we represent here by this beta IB, where beta is the current amplification factor. So beta IB, that is the current the output junction or output port gives to us, and RO, the output resistance that is given by the transistor. So output equivalent circuit is like this, and naturally if we combine these two, we get the complete AC equivalent circuit of the transistor. So this is equivalent circuit method. Nowhere we have used any H parameter, but the transistor can be represented in this way also. Now if we call the earlier circuit was like this, that using the H parameters, if you compare these two circuits, what you find out, let us see. See, at the input there is a Ri, a resistance. Here there is a HIE, which represent the input impedance or input resistance, okay. Nothing else at the input, but in this circuit, H parameter circuit, there is a term HREVC, a voltage source is appearing, okay. So what that represents? Voltage source, okay. So that is the difference. But mind well, since HRE is extremely small, HREVC is also extremely small. So we can neglect this term. Actually it represents the feedback term. It is the reverse voltage ratio. So it represents the how much voltage from the output is feedback. And since HRE is very small, we can neglect this. Okay. So HREVC can be neglected. So it is almost identical. And at the output, if we compare what we are getting, RO just like HOE, 1 upon HOE, and HFEIB here, that is represented as beta IB, which clearly indicates us that HFE is nothing but the current amplification factor. So we can analyze the circuit either by H parameter method or an equivalent circuit method. We get almost a satisfactory result. But with H parameters, when feedback is incorporated, H parameters gives us a better results to understand. Now this is the H parameter and C amplifier connection. I have tried to show you how a complete amplifier circuit can be seen. A small signal amplifier circuit. Okay. Now this equivalent circuit of this using H parameter is also possible. Just what we need to do this, that from this circuit we replace the transistor by its AC equivalent one. How? Let us see. Okay. So this is the circuit. Okay. At high frequency we know that two coupling capacitors are sorted. So R1 and R2, they are sorted to the ground. Okay. Likewise at the output, since DC sources are sorted, because we are thinking only for the AC behavior, we consider that RC, okay, it is grounded, again RO is grounded. So this circuit is of the common amplifier circuit showing the AC behavior. Okay. Now, in this circuit, this transistor, if we replace by its H parameter equivalents, we get its complete H parameter model circuit of common emitter. So the upper circuit, AC equivalent circuit, okay, not there, a transistor is there. So this AC in the circuit that shows the AC behavior, we replace the transistor by H parameter model, and simply by doing this we can generate the transistor common emitter amplifier H parameter equivalent circuit. Now let us find out the measurements of some parameters of common emitter transistor. Input impedance. Now this circuit that we have known earlierly, how we define. Okay, the input impedance, the base and emitter is in series with the HREVC, but we know that HREVC is very small. Okay, so it can be neglected, and simply the input impedance of the device is simply represented by ZB equals to HIE. The second parameter, or okay, now the overall, what is the overall impedance of the transistor amplifier circuit? We have HIE as ZB. Now it comes in parallel with the two resistors R1 and R2, biasing resistor. So from this circuit, we can see that the overall input impedance Zi of this circuit is ZB in parallel with R1 in parallel with R2. So ZB that we call is at HIE here. So the input impedance of this circuit is HIE in parallel with R1 and in parallel with R2. Now this is the output circuit of the earlier circuits, and here we see that HOE is the only thing that appears between the collector and emitter as far as the transistor is concerned. And since the output voltage has very little effect, okay, on the input, okay, we can do like this. Okay, so the output impedance is simply represented by 1 upon HOE. RC and RO, they can be combined to give an output impedance only when we consider the circuit as a whole. Only when we consider the circuit as a whole. Now, like this. So the actual output impedance of the amplifier is then what becomes ZO, that is 1 upon HOE, in parallel with RAC. What is RAC here? That I have defined, that it is the parallel equivalent of the parallel combination of RC and RO. So that is RAC. Now the voltage gain, the parameters, okay, it is very easy to define, as we know, output voltage divided by input voltage, and from this H parameter equivalent circuit, how it can be found out, that the voltage gain, that is nothing but output voltage which is given by IC into RAC. If you look at the circuit, the current and voltage, and at the input IB into HIE, that is the input voltage. If we replace IC and IB by HFE, IB, okay, and then RAC, we simplify it as minus of HFE, IB will cancel, RAC upon HIE. Now what this minus sign over here representing, that it indicates that in common emitter mode, input and output signals are out of phase. Okay, that you can see in this figure, that if the input is like this, then the output is like this. So they are 180 degree out of phase. So this minus sign just indicate that. Okay, now if you look through this animation, that you can see that as the input voltage is increases, okay, the output voltage will have the opposite phase, that it is decreases. You can see carefully the motion of the input voltage and corresponding motion of the output voltage. Okay, so that is how that minus sign appears. And the current gain, finally, the output current divided by the input current, that is HFE divided by IB, and that is simply HFE. And the transistor power gain, the final parameter for a transistor, that output power divided by input power. If you look this circuit carefully, you can find out that output power is VO into IC and the input power is VI into IB. Slightly rearranging, we get the transistor power gain as AV, that is the voltage gain of the transistor by itself, into the HFE. Okay, and now the overall power gain as a whole of the circuit, AP, that is voltage gain into the current gain. Mind well, but the current gain here is not of the transistor, but it is the overall current gain. Now AC equivalent circuit that we have seen. Okay, this is just remind you what happens when we look the circuit as an AC point of view. Now this is one example how we can find out particular value of H parameters. A small signal amplifier, okay, with these values, you can see beta of the transistor is given, input impedance is given, R1 and R2 are there. So input impedance, we have already discussed the formula, ZB in parallel with R1 in parallel with R2. By taking the values, we can simply calculate it and find that for this circuit it is 1.5 kilo ohm. So by these simple calculations we can find out that. Likewise, the voltage gain of the circuit with these parameters, it can be finded out. So first, like this, first of all we need to find out the RAC, that is the effective resistance at the output, that is the equal to the parallel combination of RC and RO. So and that RAC, by taking that parallel combination in this circuit, it turns out to be 3.38 kilo ohm, and using that values, putting in the formula of the gain, voltage gain minus beta RAC, it turns out to be 253.5. So in all, what we have seen, starting from some fundamentals, we have seen transistor as a two-port network system. We have gone through the definitions of various H parameters of a transistor in CE mode, H parameters of a transistor in a as a whole, and then AC equivalent circuit method and H parameter equivalent circuit of the method that we have seen. Okay, and I hope that this terminology will help you to understand the H parameters and application of H parameters in the your electronics analysis of the circuits. Now for this we have taken the reference book. You can see more details, or you can find out more images and more methods in the book Basic Electronics and Linear Circuit, a very good book for the physics as well as the electronics students. You can go through it and enjoy it. It is very nicely a narrated book with this kind of circuits that what I have shown you. You can go through that book and you can understand what H parameters are and how they are important in circuit analysis. The book is written by the three members, Bhargav, Vasisht and Kulsist. It is a very well-known book of the electronics. You will find out in your physics library also, or in electronics library also. But I recommend that after attending this, if you go through that book, Basic Electronics and Linear Circuit, this will make more clear things to you. Okay, so this was what I have to deliver to you. Thank you BISAG and the authorities for granting me the permission, and wish you again a very happy new year and a good success in your career. Thank you.